So sometimes with integration, we come across an integral that we can't even figure out at all. So what happens in that case is we try to make rectangles. We made the rectangles earlier. We found the upper bound and the lower sum, upper sum and lower sum. That's how we did it before to get an estimate for the area. But there would be a better shape to use even than rectangles, and that shape is a trapezoid. So if I'm trying to do this problem right here with trapezoids, and based on having 4 different trapezoids, so I'm trying to find the area bounded by the curve, bounded by the x-axis from 1 to 3. I could create the rectangles, like I said, and find upper sums and lower sums. But we could also create these trapezoids. And see how that would give us a very nice, accurate estimation for the area. And the more trapezoids we have in there, the more accurate our area estimate is going to be. The reason we need another way on this problem is because if I try to do this problem using our rules, this would be a rewrite for this integral. 1 over x is x to the negative 1. If I add 1, what would I get? What's negative 1 plus 1? 0. And then I would have to divide by 0. That has no meaning to it. So I cannot find this integral by using a simple integration rule. A u substitution isn't going to work on it either. And so that's why we need another way to find that area. And another way that we can find the area is with this trapezoidal rule. The formula to find the area of a trapezoid is base 1 plus base 2 divided by 2 times the height. We don't really need to know that though, because what happened was those early mathematicians who were working with these integrals, they found out this rule that's based off of finding the areas of all these trapezoids. And what the rule ends up being is b minus a. So the top number is b, the bottom number is a. Divided by 2 times n. N is always going to be given to us. So in this case, n is 4 in this problem that we're trying to do. But if we had n is 8, n is 12, n is 1,000,000, the more n's we have, the more trapezoids we have, the more accurate our area estimate will be. But we're going to go with n being 4. So the way we do this then is I'm going to have to do b minus a. So once again, we're doing this problem. So here's our b. I have to do 3 minus, here's the a, 1, divided by 2 times 4, which is 8. So this b minus a over 2n is going to end up being 2 over 8, which is 1/4. So our area approximation is 1/4. And now I just have to follow this formula. It says f of x sub 0. That means starting with this value, this is x sub 0. What do I get if I plug it into the function? Well, 1 divided by 1 is just 1. So my first value right here would just be 1. Now I have to do plus 2 times, now so this right here, like I said, this is 1, this is 1.5, this is going to be 2, this is 2.5, and this is going to be 3. Those are all the values that I have to substitute in to find f of x sub 1, f of x sub 2, etc. Whatever our n value is, then n plus 1 is going to be how many terms we're going to end up with. So we're going to end up with 5 terms. I have 1 term, I go to my second one. It's going to be 2 times whatever I get when I plug in 1.5 into my function. So I have to do 1 divided by 1.5. What is 1 divided by 3/2? 2/3. So I'm going to have 2 times 2/3 for that next one. Plus 2 times. So I've already done this one. I already did this one. Now I go to my next point, which is 2. and I have to plug it into my function. 1 over 2 is 1/2. So 2 times 1/2 plus, I have to do 2 times again, and I go to my next point. I just did 2, so I go to my next point, which is 2.5. What is 1 divided by 2.5, or 1 divided by 5/2? 2/5. So I just plugged in 2.5, so I go to my next point, 3, and it's going to be plus. Notice now there's no coefficient once I get to this last term. So I don't do another 2. It's just plus whatever I get when I plug 3 into this function. So 1 over 3 is 1/3. So at this point, I can just use my calculator. I'm going to simplify a little bit first. So I have 1/4 times 1 plus 4/3 plus 1 plus 4/5 plus 1/3. So typing this in, 1/4 times 1 plus 4/3 plus 1 plus 4/5 plus 1/3. And I get this answer, 1.117. Okay. Now, guys, remember what we were doing here. We needed to know the f of x values for 1, 1.5, 2, 2.5, and 3. Here's another way you can find those values. See, I just plugged them back into the function to find the values, but you could also do this. You could go to y equals, put in your function, 1 divided by x. You can go to your table, and your table is probably set up like this. Everybody get out your calculator and look at your table. See, I want my table to tell me what is y when x is 1, what is y when x is 1.5, etc. So what I can do is I can go to second window, and I can tell this I want my table to start with an x value of 1, and I want my change in my table to go up by 0.5 every time. And so now when I look back at my table, here are my answers for y. So I got 1, and I have to recognize this. If I get 0.6 repeating, I have to recognize that's 2/3 because I want to use exact values. When I plug in 2, I get 1/2. When I plug in 2.5, I'm getting 0.4, which is 2/5. When I plug in 3, I'm getting 0.3 repeating, which is 1/3. Do you see that's how we did this? This was f of x, so my first y value, plus 2 times my second y value, 2 times my third, 2 times my fourth, and then just my fifth term. And that's going to give us a good estimate. So that's the answer when I use the trapezoidal rule. So the trapezoidal rule is one way to estimate the area. Then another mathematician came along by the name of Simpson, and he said, hey, I have a better, more accurate way to do this. And he's like, if you do b minus a over 3n, and then use this pattern where you just use the first y and then 4 times the y, 2 times the y, 4 times the y, 2 times the y, 4 times the y, as many times as needed until you get to the end, this is a more accurate estimate. So let's see how this would work then. I'm still doing this for the same problem. N is still 4. So I'm still using the same. I have to start at 1. I have to have a total of n being 4, which means I need 4 additional spots added onto this, and I have to end at 3. So if I need an additional 4 on top of the 1, I can do 3 minus 1 is 2, divided by 4 is 1/2. That's how I can figure out what my intervals are. What's the difference between these two? divide by n, and that's going to be our interval. So I have to add on a half, add on a half, add on a half. And again, we're using the same x's, we're plugging them into the same function, so it's going to be the same y values. I'm not going to bother recomputing those. And now it's just a matter of following the formula. Here's B, here's A. So the area is going to be approximately equal to B minus A, that's 2, over 3 times n this time. So 3 times 4 is 12. F of x sub 0, that means my first value is 1, plus 4 times my second value, 2/3, plus 2 times my next value, which is 1/2, plus 4 times my next value, which is 2/5, plus, and then the last y value I use is just whatever it is. I don't change it at all. So it's just 1/3. See the pattern here? Coefficient 1, 4, 2, 4, 1. I will not ask you to memorize this. I will give it to you. It will be on the quiz. But I will expect you to be able to apply it and get that good estimate for the area. So finishing this, 2 over 12 is 1/6. 1 plus 8/3 plus 1 plus 8/5 plus 1/3. Just go over here. 1/6 times 1 plus 8/3 plus 1 plus 8/5 plus 1/3. And I get an answer of 1.1. I should use approximately. Okay? So with this one, we have an estimated area of 1.117. This one, our estimated area is 1.1. Now they say use your graphing calculator to compute this. So this is what I was talking about earlier. We go to y equals, we already have 1 over x in there. We go to second trace, I go to number 7, and my lower limit was 1, my upper limit was 3, and it tells me that this area is 1.099. So you can see that both of these give us very good estimates of what the area is. Again, the calculator, though, is only giving us an estimate of the area. If we could actually do the calculus and integrate this, which we will learn a special rule for this later on, but there is a rule to find this integral. We just don't know it yet. As I showed you, with all the rules we know, it doesn't work to find the integral. But all of these are giving us very close estimations. Questions about it? All right. So you have to practice this. This is not a difficult thing, but it will seem difficult if you haven't practiced it at all. So let's go ahead and get out your book.